Hey, this is Mr. Roosevelt. Today we're talking about Activity 8, how atoms interact with each other. I'm glad you're here. Let's get some music going. We're walking through this chapter. We're going to talk about the stuff in the investigate section. And we're going to start with, first you need a handout, so you're going to write down, take some notes from what we're doing today. And start with the entry task. So take a few minutes. What do you think about this question here? So we've learned a little bit about the chemical behavior of an atom, and that is determined by the arrangement of an atom's electrons. Not neutrons, not protons. It's electrons that are key when it comes to chemical behavior. And in particular, it's valence electrons. For example, the salt we put on our food, we all know this, sodium chloride, NaCl. Here's the question. How do you think the valence electrons of sodium and chlorine interact to create the bond? Write down some ideas, take a few minutes, put them on the worksheet in the square that I've given you space for. And then if I come around and talk to you, you'll have an answer for me, okay? So take a few minutes to do that. Okay, thanks for doing that. Let's get started. We're on page 425 in the book. I'll put the chapter out on the Q drive so you can take a look at that. This video was on the Q drive. Oh, I've also got the periodic table with the electron configuration. Remember, that's one of the key periodic tables that we're using right now. So get those resources up on the screen there so you can use them, and let's get going here. So you'll remember from the last activity we did that we were talking about ionization energies. Can you say that? Ionization energy. Okay. Little reminder here. That's the amount of energy it takes to remove one electron completely, like rip it out from an atom. We had a graph. It kind of went like this. There were some atoms that had the lowest ionization energy. Where were those located on the periodic table? Do you remember? Alright, so here's a quick refresher. We had this chart. It wasn't in color, I guess, because you had a copy. But anyway, the blue line is the first ionization energy. How much energy it takes to remove the first electron from an atom. You remember tracing over this or thinking about this. And then we'll also talk about, in a few minutes here, the second ionization energy. But first, which atoms have the lowest ionization energy? First ionization energy. So which on the blue line are the lowest atoms? Can you take a look at this and tell me what you think? Alright. What you should have said is lithium, sodium, potassium have the lowest ionization energies, first ionization energies of all the elements, the first 36 or so on the periodic table. Okay? Good job reading this graph. So that's one part of the answer. Where are these on the periodic table? That's the next question. So here's a snippet. They're in group 1A. They're in the alkali metals group. So we know, when we look a little bit closer at these, that these elements here, they're built off of the last noble gas. So just to the left, you have to kind of go back to the other side of the table. That's where they are. So 1s2, that was helium. And so lithium has one electron in the s sublevel of the second energy level around that atom. Yeah, you remember this. And then sodium is built off a neon, and it has one electron in the s sublevel of the third level above neon. And then krypton is the same way, as one electron. So here's what you should think. You should think that electron's kind of lonely, and it's not really getting into the party with lithium or sodium or krypton, so, or sorry, potassium, so it's willing to jump. It's willing to bail out of there. Alright? So that's the answer for 1A. Let's go to 1B. What do you observe about the amount of energy required to remove the second electron from atoms of the elements defined in A above? So take those atoms, lithium, sodium, potassium. Take a look at the graph for second ionization energy. Ready? So there's second ionization energy. Remember, it's that orange dotted line, right? Where are those ones that had the lowest first ionization energy? Can you find those? Oh, I see one. You see them? Here we go. There. That's right. They've gone from being on the bottom to the top. Started on the bottom, now they're at the top. The whole gang's here. Anyway, lithium, sodium, potassium, they're at the top. That means their second ionization energy is huge, relatively speaking, which means after you remove one electron from lithium, sodium, or potassium, they reach a somewhat stable configuration. That means they don't want to lose any more electrons. And that makes sense because they've become kind of like the noble gases just ahead of them, right? Lithium's become a little bit more like helium. Sodium's become a little bit more like neon. Potassium's become a little bit more like argon. So that's 1B. Let's go to 1C. Use your understanding of the arrangement of electrons in the group of elements to suggest a reason for the pattern you noted in B. Alright, so I think I probably already answered this, but let's go over it one more time. Alright, since the alkali metals, I'll read this to you, get more stable after you remove the first electron, that means they show up on a peak after you remove one electron. It takes much more energy to remove the second electron. That's what a peak means. That is what the first and second ionization energy graphs are telling us for the alkali metals. So the alkali metals, lithium, sodium, potassium. Once you remove that first electron, they just do not want to lose another electron. They are very reluctant to do that. And that means that they've gotten more stable. So you can imagine, if you go back here, what would happen if you removed... So we know beryllium, you could remove beryllium's atom. First atom, beryllium would be fine with that. And look, beryllium would be fine if you removed a second electron from that atom. Same with magnesium, same with calcium, but I'm giving it away. So let's keep going. Which atoms have the smallest values for second ionization energies? Where are these atoms located on the periodic table? Alright, take a look. Second ionization energies. That's the orange curve with the dotted line, right? Which atoms have the lowest? Which atoms are the lowest here on the second ionization energy curve? I think you can see beryllium, magnesium, calcium. Right. And now check it out. Where were those for first ionization energy? Oh, well, where are they on the table? Well, we know they're in group 2. Alkaline earth metals, beryllium, magnesium, calcium. Group 2. Alkaline earth metals. Also, sometimes we call it Roman numeral 2, 2A. Take a look at the electron configuration. We'll talk a little bit more about that, but take a look. It's just like, it's only 2 electrons above neon, magnesium, and it's only 2 electrons above argon, that's calcium. But where were these guys for first ionization? Let's take a look. Oh, right. They also had low first ionization energies. So that means these guys, they have 2 electrons, but they're just going like, yeah, take these 2 electrons. I don't care. I'll be fine. Take them. All right. So there's a little bit of discourse here on question number 2, investigate number 2, page 425. Let's take a look at this. I'll read it. Once you recognize the role of an atom's electron arrangement, especially the valence electrons, in an atom's chemical activity, so valence electrons, key for chemical activity, and it's the atom's arrangement of electrons that make them valence electrons. They're the outermost electrons. You can predict formulas for compounds which are formed by the chemical elements. Oh, I forgot to say, at the end of this video, there's a little game. There's some cards coming at you, and you gotta, tell me a little bit what they do. So stay tuned for that. It's a game. Recall that the valence electrons are the electrons located in the highest energy level, and these levels are designated by the sublevel that has the highest numbers. So those first numbers, take a look at this. These are the valence electrons, 3s1. There's only one. Ha! 3. That's the highest energy level too. 3, because neon had 2 and 1s2, 2s2, 2p6, and then So 2s2, 2p6, they'd made 8 for neon. Anyway, I'm going off track here a little bit, but sodium has 1 valence electron. Which you can see from this, from the electron configuration here. And that's what this paragraph says here. Sodium has 1 valence electron in a 3s sublevel. By losing that electron, the sodium atom becomes a sodium ion, and it has the same stable electron arrangement as neon. Hey, what is the electric charge on the resulting sodium ion? Ooh, I know this. I take away 1 electron from an atom that normally has no charge. That means I have more protons now than electrons. I think I know this. +1. If you said that, tell your neighbor that you know this stuff, okay? Next question. Let's take a look at chlorine. How many valence electrons does chlorine have as an atom? Okay, I'm thinking here valence electrons. They are the electrons in the highest numbered sublevel. So in this case, chlorine has 3. That's the highest level sublevel. It has S sublevel, though, and a P sublevel. It has 2 in S and 5 in P. I think I know what I do. Oh, it's also in group 17. 7A, 7 valence electrons. Nice work. Give yourself another pat on the back there, right here. Oh, okay, good job. All right, 2B, page 425. How many electrons does a chlorine atom need to gain to have the same number of electrons as an argon atom? Oh, so hang on a second. Oh yeah, okay, so if chlorine is here, if it could have 1 more electron, it would be argon, be totally happy from, you know, a valence electron point of view. So it looks like just 1. Yes! Okay, 1. When a chlorine atom gains an electron, a chloride ion is formed. An ion, do you remember? Definition of an ion? Yeah, it's an atom that has gained or lost some charge. Since the original, so that means it has a positive charge or a negative charge. Since the original chlorine atom was electrically neutral, neutral means the number of protons was equal to the number of electrons, so they balance each other out. They cancel each other out. That's neutral. And it gained a negative electron to form the ion. Gained a negative. Okay, what is the electric charge? What's the sign and how much is on this chlorine or chloride atom ion? You ready? You got it? There it is. 1 minus, -1. Okay, nice job. That's investigate 2C. Each chlorine atom is capable of accepting 1 electron. Describe how you think the compound sodium chloride NaCl is formed. All right, so check this out. Here's a quick hint. You remember this little picture we had? The sodium chloride romance. It looks like this guy right here had 2, 6, 2, 4, 6, 8, 10, 11. Sodium has 11 protons, which means for a neutral atom it has 11 electrons. This guy over here is 5, 9, 5 is 14. This means it's got, wow, this means it's got 5, 9, 14, and then 16, 17. It had 17 on the outside, but now it's grabbing one because it would really like to have 18. That's a hint. Let's see. All right, chlorine, here's the answer. Chlorine liberates an electron from sodium. That means it grabs it. Since sodium has a low ionization energy, that's why that's possible. That makes an Na plus ion, all right? But chlorine, having gained an electron, is now a Cl1 minus. That means it's a chlorine, it's a chlorine negative ion. All right, so since ions have opposite charges, they attract, opposites attract. That forms a compound, sodium chloride, an ionic compound, which means that they have given up or gained electrons. Salt. There we go. That's the answer for number 2. Let's go to investigate number 3, page 425. Questions about zinc. What's the question? Consider the reaction between aluminum and zinc chloride, similar to the reaction in activity 3. Oh, remember the reaction in activity 3 was copper chloride and lenachlorine. Percy copper, lenachlorine, remember that? The zinc atoms in zinc chloride have 2 valence electrons located in the 4s sublevel. Hey, mister, why don't I count these 10 here in the 3D level? You can't count those because they're in a lower level. 4 is the highest level. You have to count anything that has a 4 in front. So there's only 2. Okay? Highest energy sublevel, 4. S sublevel, 2 electrons. You can note the 2 valence electrons in the electron range marked in the periodic table. That's what I just said. All right, in order to acquire the electron configuration of argon atoms, which is a rather stable arrangement, the zinc atoms give up their 2 valence electrons to form zinc ions. Hey, real quick question. Is zinc a metal, a non-metal, or a metalloid? It's a metal, right. Since the original zinc atom was electrically neutral, and it lost 2 negative electrons to form the ion, the resulting ion has a positive charge with a magnitude 2 times the charge on the electron. It has a +2 charge. So now, investigate 3A, page 426. Each chlorine atom is capable of accepting 1 electron. How many chlorine atoms that only take 1 electron are needed to accept the 2 electrons that zinc atoms have to give? Alright, so there's chlorine. It needs 1. 2, right? If you create 2 chlorine 1 minus atoms every time you take 2 electrons from 1 zinc atom, then the ratio is 2 to 1, right? 2 chlorine get 1 electron each from zinc, who's giving up 2. Here's zinc is like giving up 2. Here's 1 chlorine atom, they're happy. Here's another chlorine atom, they're happy. Okay, oh, good. Alright, so when you write the formula for a compound, 3B, hey, write these answers down on your paper, okay? So if you need to pause or go back, write them down on a piece of paper, the handout. When writing the formula for a compound, the number of atoms necessary to balance the loss and gain of electrons can be designated through the use of a subscript, such as the 2 in H2O. Stupid book. We haven't talked about how H2O has given up electrons or anything, so, alright, but anyway, the point is, we have 2 hydrogen atoms connected to 1 O. I don't know why yet, but that's what it is. So here we go. How would you write the formula for the compound zinc chloride? You ready? Zinc chloride. Remember, back here it was 2 chlorine for every 1 zinc. You ready? Bam! Zinc chloride. This means 2 chlorine atoms for every 1 zinc atom in the compound, which a compound is a combination of atoms that are called zinc chloride. All right, investigate number 4. I think this is the last question in the investigate section, which is good because we're making good time here. In a reaction between aluminum, okay, aluminum, Al, and zinc chloride, what I just wrote, zinc, ZnCl2. Aluminum replaces zinc in the zinc chloride. Okay, folks, jot down on your piece of paper, this is a single replacement reaction. We learned about this in activity 3, but this is where zinc chloride, perfectly happy, dancing together, aluminum butts in, kicks out the zinc, latches onto the aluminum chloride, so aluminum chloride are dancing, zinc is out to lunch. So, we now have a new compound, aluminum chloride and zinc all by itself. Alright, so let's see here. This is how I write this. Aluminum, all by itself, gets sprinkled into the dance hall where zinc and chlorine are happily dancing. Actually, maybe zinc is dancing with 2 chlorines. That's weird. Alright, anyway, forget it. A little bit problematic. It makes, look here, the aluminum, this is so good I gotta like draw a little line here. So aluminum boots out the zinc, like, see ya, takes its place. So now there's aluminum with the chlorine. And zinc, who got booted out, is over here all by their lonesome. This means that a reaction happened. The question marks mean, hey, mister, what numbers go there? Well, you can tell that I put question marks there because maybe I didn't know when I made the question. But anyway, the point is, you could put anything there. You have to figure out what makes this a balanced equation. What's balanced? What's he talking about? All right, stay tuned. Here we go. Just relax. 4a. Consider an atom of aluminum. Okay, I gotcha. How many valence electrons does aluminum atom have? Well, let's see. Where is aluminum? Ooh, there it is. Here. Aluminum is over here. It's in group 13. I remember something about this 13. There's a 3 here. There's a 3 here. Oh, I know. Aluminum. Ooh, it's not going to gain 5 electrons to get to argon. It would rather. Ooh, let's see. 3s2, 3p1. Probably would rather lose 3 to get to neon. So it has 3 valence electrons because it wants to lose 3. Exactly. Nice job. How many electrons does an aluminum atom need to give up to reach the same chemical stability as a neon atom? That's the same question. Same question. When I ask you how many valence electrons, in a sense, I'm asking you how many electrons would have to lose, or how many would have to add to make 8. But anyway, okay, so 3. Oh, aluminum would gladly give up 3 electrons to be the same as neon, or to be equivalent to neon as far as electrons go. Hey, remember there's a whole bunch of table over here, but aluminum would jump all the way back and then go back up here to this row. Would gladly lose those. You ready? What are aluminum atoms called after they give up their valence electrons? What's their electrical charge? Ooh, hang on. Aluminum has no charge. It's neutral when it has the same number of protons as electrons. But I'm losing 3 electrons. That means I'm taking away 3. That means I have more protons. Are you ready? Here we go. Let's do it together. Aluminum is built on neon. Electron configuration is the same up until neon, and then it adds a 3s sublevel, a 3p sublevel. There's the 3s, there's the 3p. It has 2 electrons in the 3s, has 1 electron in the 3p. It's going to give up 3. It's going to become Al3+, which means an aluminum with a 3+ positive charge. How many chlorine atoms are needed to accept the electrons given up by the aluminum atom? Oh, okay, I gotcha. Aluminum's given up 3 electrons. Chlorine is like waiting for them. Chlorine. I like electrons. I like electrons. I think if chlorine, it only takes 1 each. I think if every aluminum atom gives up 3 electrons, every chlorine atom needs 1. That means I probably have 3 chlorine atoms for every aluminum atom. That means when the dance happens, I guess I had it twice. All right, that's fine. That's fine. How would I write this formula? You ready? Boom. For every aluminum atom, you need 3 chlorine atoms. You'd write it as AlCl3, aluminum chloride. So here's the final formula. I had aluminum sprinkled into a dance hall where zinc and chloride were happily dancing. Here they are right here. And I put aluminum in there. These guys were totally happy. Remember, let's do this. Zinc and chloride are happily dancing. Or zinc is dancing with 2 chlorines. Okay, I gotcha. Aluminum butts in. Boom. Zinc gets booted by aluminum. Aluminum takes zinc's place. But you need 3 chlorines now for every aluminum. And when you bumped zinc off, so the 3 here means it's kind of like algebraic multiplication. There's 3 of these molecules in here, 3 zinc chlorides. That means there's 3 zincs, and there's 3 times 2 chlorine. So that means I have to have 2 times 3 chlorine. 2 times 3 is 6. So I have 6 chlorine here. And then 3 zinc over here, 2 aluminum here, 2 times 1 aluminum, 2 aluminum there, and then 3 zinc out there, 3 zinc there. Good. Nice. They balance. Here's what we just did. You read this equation like this. 3 molecules of zinc chloride added to 2 atoms of aluminum yields, the arrow, 2 molecules of aluminum chloride and 3 atoms of zinc. Nice. Here's what we just did. You use the conservation of mass by Lavoisier and use the law of definite proportions from Dalton. Yes. All right. So, let's play a little game about this. So we've been talking about ionic compounds. One atom, it's usually a metal, gives up an electron to another atom, which is usually a non-metal. So let me show you 2 cards. You're going to tell me if they form an ionic compound. Are you ready? Here we go. Do these 2 atoms form an ionic compound? Hydrogen. All right, there's a lot of information there. Here's where I want you to take a look. Take a look here. Oxidation states. This means hydrogen plus 1. Does that mean it gains electrons or loses electrons? Hydrogen's over here. Plus means loses electron. Chlorine, as we've said, gains an electron. If they match up, aha, they do. Yes, hydrogen can give up an electron and chlorine takes electron. So these guys form an ionic compound. Yes. You ready? Next one. Fluorine and chlorine. Alright, I'm looking at them here. Well, I see ones. Fluorine wants to get an electron. Chlorine wants to get an electron. These guys are not going to dance together. If they both want to take an electron, there's no giving in this relationship. There's just taking. That just does not work. Alright. How about these? Fluorine. Hydrogen. Alright. Fluorine wants to get an electron. Hydrogen can give an electron. These are the numbers I'm looking at that tell me that. Yes! Fluorine wants an electron, and hydrogen gives an electron. Cool. You ready for the next one? Here we go. Sodium. Will sodium form an ionic compound with hydrogen? Let's see. Sodium mainly wants to give an electron. Hydrogen just wants to give an electron. 2 things that just want to give all the time and never take. You know, that doesn't work either. This doesn't work. If they both want to give an electron, there's no way they'll partner together. Alright, how about these 2? You ready? Magnesium, chlorine. Will these form an ionic compound? I tell you what, I'll give you a hint. This is Percy Copper and Lena Chlorine, because Sirius MG came along and booted you off. Yep, magnesium gives up 2 electrons. Chlorine will take, or 2 chlorine atoms each will take 1 electron from those and make MgCl2. Yes, good job. Here we go. Magnesium, aluminum. All right. Magnesium, it looks like it wants to give 2 electrons. Aluminum wants to give 3. That doesn't work. No. If they both want to give up electrons, they don't form an ionic compound. All right, here we go. Ready? Another one. Silicon and aluminum. Ooh, silicon's a metalloid. Oh boy. Aluminum's a metal. It's okay if you don't get this one, but just take a look at the letters. So this guy could, silicon, notice he could go +4 or -4. Aluminum could go +3. So if I took a -4 and took a +3, I could, and if you Google this, you will find that silicon is aluminum silicide, they call it, and it is an ionic compound. Alright, you ready? Here we go. Sulfur. Can sulfur form an ionic compound with fluorine? Alright, so fluorine, check this out, wants to take an electron. So these are those people, they're always taking, never giving. No, they do not form an ionic compound because they both want to grab electrons. That won't work. How about these 2? Sulfur and sodium. Ha! Of course! Sorry about that little PowerPoint problem there. Sodium wants to give an electron. Sulfur will take 2. You can get sodium sulfide from this. Excellent. So now, here's a little question for you. Take a look at these pictures at the bottom. These are actually showing you the valence electron. So neon has 1 valence electron by 1 dot. We're going to talk about dots a lot next week, or coming up. Just wait. Sulfur has 2 empty spots because it has 6 valence electrons. It means it needs 2. So this is almost a hint, like, hey, if you could get 2 of these guys together, plug them in here to these spot for 2 here, you could get an ionic compound. And that, my friends, is electron dot notation. We will talk about that soon. So thanks for listening.